Good morning, everyone. This video we are talking about linear programming, section 10.7. We are going to have 3 examples. Example 1. Each bag of nuts contains peanuts and cashews. The total number of nuts in the bag can't exceed 60. There must be at least 20 peanuts and 10 cashews per bag. There can be no more than 40 peanuts or 40 cashews per bag. What is the region of constraints for the number of nuts per bag? So you can see the goal of this word problem is to find the region of constraint. We will understand the concept during the course of explaining this example, okay? Well, this is an application problem. The goal is to find the region of constraint for the number of nuts per bag. Every bag, you have 2 types of nuts, peanuts and cashews. Then we need to find the restraints for the number of peanuts in the bag and the number of cashews every bag. So we want variables. The first thing to do is always to bring in variables and use your variables to represent your goal. Let x and y be the, how about this? Let's say every bag has x peanuts and y cashews. X and y are the number of peanuts and cashews per bag. So we need to find the restraints on the variables x and y. So we have some information in the problem. Let's try to translate them. Each bag of nuts contains peanuts and cashews. The total number of nuts in the bag can't exceed. How do you understand can't exceed? Exceed means bigger than, right? Can't exceed means less than or equal to, or no more than. Do you agree? The total number of nuts in one bag. Every bag has 2 types of nuts, peanuts and cashews. Now we know every bag has x peanuts and y cashews. So how do you translate this sentence? The total number of nuts in a bag can't exceed 60. Would you have x plus y less than or equal to 60? Does that make sense to you? Because the sum of x and y is the total number of nuts in a bag, which cannot be more than 60, so it's less than or equal to 60. So let's read on. There must be at least, what does at least mean? At least means bigger than or equal to, right? At least 20 peanuts and 10 cashews per bag. Okay, actually this sentence gives us the lower bound for the number of peanuts and the number of cashews per bag. Lower bound. So the number of peanuts per bag at least be 20, so x has to be at least 20. At least 20. And the number of cashews, which is y, at least be 10. So far we have 3 restraints. So now you understand what is a constraint, right? Constraint. Let's keep reading. There can be no more than 40 peanuts or 40 cashews per bag. And this sentence actually tells us the upper bound. for the number of peanuts and cashews every bag. X is the number of peanuts every bag. Cannot be no more than, can be no more than, sorry. There can be no more than would be less than or equal to, right? So the number of peanuts every bag is less than or equal to 40. Same with cashew. The number of cashews every bag, which is Y, also no more than, so less than or equal to 40. Yeah, so those are the information that we have from the problem. From the information, we have 3 constraints or restraints. Either way, I think they mean the same. So for more convenient, I'm going to rewrite the 3 inequalities. The first one, x plus y less than or equal to 60. Second one, I want to switch the order. X is between 20 and 40. Number 3, variable y is between 10 and 40. Alright, so now we are looking at a system of linear inequalities in 2 variables. In 2 variables, then the solution set of the system is going to be a region in a 2-dimensional space. We have 2 variables, so the solution is going to be, if the system has any solution, the solution is going to be an ordered number pair. Okay, you know what I'm saying? So for example, if x, y both equal to 15, would that be okay? 15 plus 15 equals 30. 30 is no more than 60. That is fine. 15 is between, oh, that doesn't work. So I'm going to change x, the value of x, to 25. 25 and 15 add up to 40. 40 is no more than 60. The first inequality is satisfied. 25, the value of x is between 20 and 40, so the second inequality is satisfied. Value of y, 15, is between 10 and 40. The third inequality is also satisfied. So yes. So this is a solution. This is a solution of the system. So we can know, you would know there are many, infinitely many solutions for the system. And the solution set of the system is the overlapping part, the common part of the solution set of number 1, solution set of number 2, and the solution set of number 3. So here we are going to graph the solution set for each single inequality, and then look at the common part of them. So let's see, how do we do that? We are going to draw a graph. Because all the values of x and y, they are positive, because x and y represent the numbers of peanuts and cashews in the bag, so we only consider quadrant 1 in a rectangular coordinate system. Okay, actually we only consider quadrant 1. We only need to consider quadrant 1. So let's graph the first inequality. Let's graph the first inequality. The first inequality is x plus y less than or equal to 60. Anyone can tell me what's the boundary of the solution set of this inequality? Do you remember how did we find the boundary? Simply change the inequality symbol to equal. Then we have x plus y equals 60. And that's the boundary of the solution set of inequality 1. And this is a straight line. We understand that, right? X plus y equals 60 is a straight line. That straight line is going to be the boundary line of the solution set of inequality 1. Let's rewrite this. Well, we don't have to rewrite it, because it is so easy to find the x-intercept and the y-intercept to graph this straight line. As x equals 0, what is y? 60. As y equals 0, what is x? 60. You see how convenient it is. If the straight line is in the standard form, we can find, most of the cases, we could find the x-intercept and the y-intercept. This is x-intercept, this is y-intercept, so easily. Then let's plot those 2 points. 60, 0. I would say, let's say this is, how about this is 60, and this is 60. So this is 60 comma 0, this is 0 comma 60. We connect those 2 points, we would have the boundary line. Are we gonna draw the boundary line as a dashed line or dotted line or a solid line? Since the inequality symbol in the original inequality is less than or equal to, we are going to graph the boundary line, this line, solid, because the points on the line are solutions of the system. So we are going to, what color? Let me just use black. Connect them. So that's the boundary. Okay? And yeah, so that's the boundary line of the solution set of the inequality 1. We're still talking about number 1. And then what's the solution set of the inequality, the original inequality? The boundary divided the whole plane into two parts, right? We talked about this before. The part above and the part below. We only need to find a testing point to determine which part. So we're gonna try the origin. As we have learned before, always choose origin as long as the origin is not on the boundary. So in this case, origin works 0, 0 because it's so convenient. So if we plug in 0, 0, if we plug 0, 0 back into the original inequality, let's see what would happen. 0 plus 0 less than or equal to 60. The inequality is satisfied. Means 0, 0, the origin is a solution. So we should have the solution set for inequality 1, the half plane below the boundary, okay? Half plane below the boundary. If we only look at the inequality 1, half plane below the boundary. Now you see a line segment, but actually the boundary is a straight line, okay? Once again, the solution set of inequality 1 is the half plane below the boundary line, this one, including the points on the boundary. All right, so we are done with number 1. Let's move to number 2. Number 2 only has the variable x. Oh, that's fine. But number 2 is a compound inequality. X is between 20 and 40. So the solution set of the inequality is going to have 2 boundaries. The first one, remember, how do we find the boundary? Change the inequality to equal. X equals 40. Change this inequality to equal. X equals 20. So the solution set has 2 boundaries. The 2 boundaries are 2 vertical straight lines. Okay, so if this is 60, then 1/3 of it is going to be 20. This is going to be 40. So x equals 20, x equals 40. The 2 vertical straight line going to be the boundary of the inequality number 2. Let's graph it. When we graph them as a solid straight line, because again, the original inequality symbol contains the equality. Means the points on the boundary line are part of the solution set. So we use black. We graph this straight line, solid, and then we graph this straight line, solid. Okay? So you can see the 2 straight lines, of course, they are extending indefinitely. The 2 boundaries form a bandage region, like it's extending infinitely upwards and downwards. It is a bandage, is a bandage region. So inside the region, that's a bandage. Outside, we also have many points, right? So is the solution set of the inequality number 2 the region between the 2 straight lines or outside the 2 straight lines? We can try to find a testing point. we can try to find this point. That's gonna be 30, right? 30, 0. It's okay because 30, 0 is not on the boundary. So any points, as long as it's not on the boundary, could be chosen as a testing point. Let's plug in. Really doesn't matter the y value because the y doesn't appear, doesn't show up in the inequality. We plug in 30 here. 30 is between 20 and 40. So yes, this point is a solution. So we determine, okay, the solution set of inequality number 2 is the region between the two vertical straight lines. One more time, the solution set of inequality number 2 is the region between the two vertical straight lines, including the points on the two vertical lines. Am I clear about that? Number 3 only has a y variable. Number 3, y bigger than or equal to 10, less than or equal to 40. How do we find the boundary? Now you should know, right? Just change the inequality symbol to equal. Y equals 40, this one. Y equals 10. Those two straight lines are the boundary of the solution set of the inequality number 3. Let's graph the two boundaries. We're going to graph them as a solid line. Same reason, because the original inequality symbol contain the inequalities. Y equals 10. Y is 10. And 40. So if this is 20, this is 40. This is 20, then 10 is going to be here. So y equals 10, sorry. Y equals 10 is a horizontal straight line. Okay, horizontal straight line, y equals 10. Y equals 40, also a horizontal straight line. Hold on, let me see if this is 20. Yeah, so this is gonna be this way. Because this point has a y value of 40. Yeah, let me put 40 a little bit higher. So this is a y equals 40. Alright? So yeah, maybe a little bit confusing now because too much. So look at the two horizontal lines, y equals 10 and y equals 40. The two straight lines, the two horizontal straight lines divide the whole plane into two parts, the region between them and the region outside them. And the solution set is gonna be the region between because it's very easy to figure out. We can try 0, 20. We can try this point as the testing point. The value of x really doesn't matter. Just for convenience, I choose x equals 0. And the y value is 20. 20 is between 10 and 40. So the solution set includes this point, testing point. And this point is between the two horizontal straight lines. So the solution set of number 3 is the region between the two horizontal lines. One more time. The solution set of number 3 is the region between the two horizontal straight lines, including the points on the line. Okay, so you would remember what I said for the solution sets of all the three inequalities, right? And now we need to find the common part. What is the common part? What's the common part? The region below this straight line and between the two vertical lines, between the two horizontal lines, you should see that this trapezoid region, this region, that's the solution set of the system. Okay, that's the solution set of the system. And that region is called region of constraint. Region of constraint. There's another name for the region of constraint. It's called planar. This is also called a planar, feasible region. This is just different names for the same thing. Planar is like a two-dimensional. Plane is a two-dimensional space, right? Feasible means the value of x and y could only happen in that region, and it is a region. So that is called a planar feasible region as well. Sometimes we can just say that's a feasible region. Also called the region of constraint. Is the solution set of the system. The system includes all the constraints on the variables x and y. So are we clear about that? Since it's almost 20 minutes, I'm going to stop here and start a new video. I'll see you in example 2.